In this video, we're going to see what happens when we combine the three gas laws from the previous lesson and make one equation that we can use for any scenario. First of all, let's remind ourselves of the three gas laws. So the first one that we'll look at is the relationship between volume and temperature. That's often called Charles's law. Now, the relationship shown on this graph states that at a fixed pressure, the volume is proportional to the temperature, otherwise written as V equals kT, where K is a constant value to do with the amount of gas that you have. We can rearrange this as V over T equals K. That means if I take a quantity of dry gas at position 1 and I heat it up to position 2, that means that V1 divided by T1 must be equal to V2 divided by T2, which is the first of the gas laws. The second of the gas laws is the relationship between pressure and temperature, often called Gay-Lussac's law. This states that for a fixed volume of gas kept at a constant volume, that pressure is proportional to temperature. This can be rewritten as P equals kT, where K again is a constant based on that gas. Rearranged, we get in much the same way as Charles's law, P divided by T equals that constant. Also, in the same way as Charles's law, if I increase the temperature of that gas from position 1 to position 2 while keeping the volume the same, then the pressure must also change such that P1 divided by T1 for position 1 would equal a constant, and that constant would also equal P2 divided by T2. So we can say that P1 divided by T1 is equal to P2 divided by T2. Boyle's law is slightly different in the sense that the volume is inversely proportional to the pressure. That means if I double the volume, I halve the pressure, or if I double the pressure, I halve the volume. Now, much the same as the previous equations, that can be written as V equals K over P, where K is the same constant we referred to in the other gas laws. Now, rearranged again, this gives us V times P equals K. So if I were to take my quantity of gas from position 1 to position 2 by changing its pressure, the volume would change such that the volume at position 1 times the pressure at position 1 must equal the constant, which must also equal the volume at position 2 times the pressure at position 2. That means we can get rid of K completely and write this as V1 times P1 equals V2 times P2. Combining them together gives us this super equation here, which contains all of the terms mentioned in the three gas laws. Using this equation, you can find any pressure, volume, or temperature, provided you know what the other pressure, volumes, and temperatures were for a fixed quantity of gas. You can see that the super equation contains all of the other equations. You have V2 over T2, you have P1 times V1, and you have P1 over T1 all involved in this equation. So let's put that into practice by looking at this GCSE question from your booklets. Now, this is an example of Charles's law. I can see straight away that the pressure is going to be kept constant while the volume and the temperature change. Now, with GCSE questions, there'll always be something kept constant. They won't change all three variables. You'll either have temperature kept constant, volume kept constant, or pressure kept constant. So keep an eye out for that in the question. What are they keeping the same? So the first part of the question here is checking your understanding of particle theory. So we should know that as the temperature of a gas changes, the kinetic energy of the particles or the motion of the particles will change. So if we're reducing the temperature, that means the particles will have less kinetic energy, they'll move around less. So we'll say that the kinetic energy of the gas particles decreases. The next part of the question is checking your understanding of what absolute zero is. So you should know that at minus 273 degrees C, that is absolute zero. And you should know that there is no energy available at absolute zero. The particles are stationary, they are not moving, so the kinetic energy is 0 joules. But it's part B I really wanted to look at with you. This question here will use the combined gas laws and show you how you can work out a missing pressure, volume or temperature based on a previous situation. So ignoring the preamble, it's about a butane gas cylinder. It's kept in a garage where the temperature changes from summer to winter. Okay, that's fine. We're interested in the numbers. So we can see a temperature of minus 3 degrees Celsius highlighted there. We can see a pressure of 3.0 times 10 to the 5. We can see another temperature, and it tells us that the volume of the gas remains constant. Then there's a number at the end there, which we don't need to use in the calculation, but we need to be aware of it. So let's label up what these numbers represent. So minus 3 is the first temperature, T1. But the problem with this is it's in Celsius and we need to put it into Kelvin. So we need to add 273 to that number to transfer it into Kelvin, which gives us 270 Kelvin. Second number here is the pressure in the winter, so we'll call that P1 in the first scenario, and that doesn't need changing. The units actually don't matter for that as long as the units for after are the same as the units for before. You must keep your units constant and the same throughout the problem. The next number shown is the summer temperature. So this is our second scenario. It's the same volume of gas, but it's in the summer instead of the winter. So T2 is 42 degrees, but we want it in Kelvin. So we need to add 273 to it, and that gives us 315 Kelvin. Finally, it states that the volume of the gas remains constant. That means V in the summer is equal to V in the winter, or V1 equals V2. So we'll just call V V for now. So now that we've summarized the problem, let's write down the ideal gas law equation. P1 times V1 over T1 equals P2 times V2 over T2. Next, we'll substitute in the things that we've labelled up above. So 3.0 times 10 to the 5 goes in the position of P1. 270 Kelvin goes in the position of T1. And V goes in the position of V because we decided that the volume was the same. On the right-hand side of the equation, we don't know P2, so we just write that as P2. That's what we want to find. V2 is just written as V, so P2 times V, and that's divided by the summer temperature in Kelvin, which is 315. As there are V's on both sides of the equation, they'll cancel out. That leaves us with 3.0 times 10 to the 5 divided by 270 equals P2 divided by 315. The next step is to rearrange to make P2 the subject, which means we need to multiply both sides by 315 to cancel out the 315 below the P2. That leaves us with 315 times 3.0 times 10 to the 5 divided by 270 equals P2. We can then just put all of that into our calculator and write down the resulting answer. This comes out as 350,000 kilopascals. as P2. Now, the question gave it in standard form, so we should probably write our answers in standard form as well. So that's 3.5 times 10 to the 5 equals P2. Now, we've done the hard bit, but we haven't finished the question yet. It asks us, will the container be able to handle that pressure? Now, it tells us that the maximum capacity of that container is 4.0 times 10 to the 5 Pascal, and our pressure only reaches 3.5 times 10 to the 5 Pascal. So the canister will not explode at 40 degrees Celsius, 42 degrees Celsius even.